Hi guys, I'm Josh Charlton and today we're going to be talking about Kirchhoff's voltage law. We're going to talk about what it is, where it's used, how it can be used, the difference between KVL in AC and DC circuits, and we're going to go through some quick examples. Gustav Kirchhoff was a German physicist who heavily contributed to the understanding of circuit theory during the 1800s. His voltage law states that the sum of the voltage drops across components within a closed circuit loop is equal to the voltage supplied. In other words, in a closed loop, net voltage is always equal to zero. And this is really just an extension on the concept of energy conservation. KVL is a universally applicable law, which is used as a basis for analyzing all different circuit types. A combination of KVL and Ohm's law can be used to solve questions pertaining to different voltage drops and component arrangements, and this combination of formulas is a basis for most simulation tools. KVL is a simple law which can have many complex applications, but it's best to consider it in its most simple sense in order to understand it, and this is easiest to do when considering all components, whether known or unknown, as merely voltage drops and working back from there. It's also important to note that accurately identifying a loop is key to getting accurate results. This presentation talks about the broader idea of KVL, so it's important to note that it's useful in AC as well as DC circuits. DC KVL is relatively straightforward, and it's essentially algebraical, relying only on identifying the correct current loop. DC circuits will be covered in the following examples. AC requires different equations and an understanding of complex numbers, since the magnitude as well as the phase of the current being supplied must be taken into consideration. Despite the fact that the equations behind each set of analyses is different, the fundamental ideas remain the same. This example shows a simple DC circuit with a 12-volt power supply, two possible current paths, and a series of voltage sources and drops. Loop number 1 has a 12-volt power supply and 1, 2, 3 voltage drops. Algebraically, we can see that the sum is equal to 0. This is a conservation of energy and an affirmation of KVL. The second current loop passes from this point through 1, 2, 3, 4 components. Note that this component is actually a voltage source. Algebraically, yet again, we can see that the sum is equal to 0, which is a conservation of energy and an affirmation of KVL. This circuit shows how Ohm's law and KVL can be combined to find an unknown resistance. Using KVL, we can clearly see that this voltage drop is equal to 4 volts, since the sum of these 3 voltage drops must be equal to 10. Using V equals IR with the known current of 2 amps, we can equate the resistance being equal to 2 ohms. This is it from me today, guys. I hope you can see how useful KVL is. Cheers.